طيب السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. We will continue inshallah talking about gradient descent. Not sure if we will finish and we'll have a chance to start a new session or not, but at least inshallah we will be done with gradient descent. The last topic that we will study in gradient descent or in linear models session as a whole is called subgradients. What do you mean by that? Some of the loss functions or the objective functions are not differentiable everywhere. Okay, so they are not continuous everywhere. There are some points where we cannot actually compute the derivative. Type. First, an example is hinge loss. If you remember hinge loss, we had something like that. We have that was y hat, and this is I think 0, and this is 1. And we had something like this, I think. So that was the loss function, the hinge loss function. And you see that when y hat is 1, it's not differentiable. Okay? But it is differentiable after 1, right? Right or not? It is differentiable after 1, right? I mean, to the right of 1, it is differentiable, right? Is it differentiable or not? Yes. What is the derivative or what is the derivative when y hat is greater than 1? What is the meaning of derivative? Yes, so what is the change of the function when we change y hat to be greater than 1? 0. Right? The value of the function is 0. The derivative of 0 is 0. Okay, it is 0. So it is differentiable, and the derivative is always 0, right? Type. Is it differentiable when y hat is less than 1? Yes. Okay. Yes, and it has a value. Okay, it has a value. Type. What is the derivative when y hat is 1? We don't, it's not defined. It's not defined. Type. Why is that a problem? Why do we care about that? In the context of gradient descent, why do you care about that? About the points that are not differentiable. What is the relationship between gradient descent and differentiable functions? Very good. It only works when the functions are differentiable. Why? Give me an evidence that it doesn't work with functions that are not differentiable. Huh? Very good. The algorithm, the update algorithm, if you remember, if we have a parameter theta, we update it with theta minus the learning rate times the gradient, right? So we have to compute the gradient. Of course, we cannot compute the gradient unless the function is differentiable. So if the function is not differentiable, then we cannot use this algorithm. Okay, exactly. We cannot use it exactly. So we have to find a solution. Type. Maybe we should only care about the functions that are differentiable, and we just ignore the functions that are not differentiable. That can be a solution. But actually, there is a solution when functions are not differentiable. When some points are not differentiable, which we call it subgradients. So we will compute what we call subgradients for the points that are not differentiable. Okay? So this solution is called subgradient optimization. So now you see the problem. The problem is that some points are not differentiable. What should we do with them? We will solve it with what we call subgradient optimization, which we will explain now. The idea in brief is that we will just ignore the problem. We will just act as if there is no problem, as if this point is differentiable. We will act as if it is differentiable. Type, what do we mean by that? We will just deal with it as if it is the next point in the function or the previous point. So we will deal with it as we deal with the points before it or after it. And we will see that very soon. Now let's take an example. This function is differentiable or not? It's not, right? There are points where they are not continuous, right? So it is not differentiable, for example, at x0, right? This is clear, right? So at x0, this function is not differentiable. But if x is a bit greater than x0, is it differentiable or not? It is. If x is a bit less than x0, is it differentiable or not? It is, right? So there is a derivative before x0 and there is a derivative after x0. Okay? The general solution, the general subgradient optimization says that you can assign the derivative, a derivative value to this point from all possible nearby gradients. Okay? So for example, all of the red lines here are lines that lie below the curve. Okay? They can look like slope to the curve, right? They are all below the curve. So this line can be a slope to that point. And that line can be a slope. And maybe also other lines. And you can do something like this, right? So all of these lines can, the slopes of all of these lines, or the gradients of or the derivatives of all of these lines can be used as the gradient value for this point, for x0. Okay? That's why here we say it's a set valued. There is a set of values that are possibly or can be possibly assigned as derivatives to this point. We can take actually any of them. The simplest way that we will do is to take either the slope or the derivative of the points, the points that are right after this point or right before that point. Okay, so in short or in brief, we will deal with that point as if this, and let me change maybe the color here. As if this line is continued this way. So this line, you see this line, the blue one? We will assume that it is continued. It's not discontinued, it is continued. And then, if that's the case, then the gradient of that point will be the gradient of that line, right? Or the derivative of that line. So that means that we will deal with that point as if it is like the points that are greater than x0. Or we can also take this one and assume that it is continued. So we will assume that this point actually lies on that line. So the derivative at that point will be the derivative of that line. Either way. So that's the solution that we will use always, or in most of the cases. Okay? We will deal with it as if it's not there. It's like an approximation. Actually, mathematically, we cannot compute the derivative at that point. But we will approximate it by the derivative of the function before or after that point. Assuming that before and after, of course, are differentiable. Okay? Is that clear? Yes, you have a question.
Are we using the red line when we put over the point, or do we just continue the blue line and use it?
Okay. The general subgradient optimization is to get one of them. Any one of them actually can be assigned.
So either the red line or continue the blue line?
Yes. That's why we say it is set valued. It's a set of possible derivatives. Okay, but usually for simplicity, we can take either the derivative of the line before, or the function before, or the function after. Okay, but actually there are more possible approximations. The more possible approximations are represented here by the red lines. Okay, any question about that? Is it clear? Okay, طيب. Let's see an example. So hinge loss, as we saw, is one of the functions that are not differentiable at some point, which is 1. If you remember here, 1 is the point where it's not differentiable. So what will we do? This is, if you look at this, this is the hinge loss function. Okay, this is L, the hinge loss function. Okay, it's always the maximum of 0 and 1 minus this part. What is this? This is, sorry, this part is y hat. Remember in the, let me do it again. So this is y hat, this is 1, and that's 0. This is 1, and that's 0. Okay, so it is the maximum of this. So if this part, which is y hat, is greater than 1, this part will be negative, right? So the maximum of 0 and the negative is the maximum of 0 and a negative number is what? 0, right? Which is the value of the function when y hat is greater than 1. So when y hat is greater than 1, the function will be 0. Otherwise, it will be 1 minus y hat, which is this part. So this part is 1 minus y hat. Okay, so that's the function, and we can see it that way. It is 0 if y hat is greater than 1. Otherwise, it is 1 minus y in y hat. Okay? Type. What happens here is that the point where y hat is 1, we add it to one of these two branches. Which branch? And if you look at this now, this is the hinge loss function, right? It has two branches. It's either 0 if y hat is greater than 1, otherwise it is 1 minus y hat. In this definition of the function, we added the point where y hat is 1 to one of these branches. Which one? Look at the definition of the branches. Which one? What are these two branches? Now, what are these two branches? Why do you have two branches here? Before and after 1, right? Because we have two, the function is like two parts, right? After, when y hat is greater than 1, it is 0. Okay, which is this case, right? When y hat is greater than 1, it is 0. Otherwise, it is 1 minus y hat. So, in this definition, we added the point when y hat is 1 to one of these two branches. Which one? Which branch? The upper branch or the lower branch? Where is y hat? This is y hat is greater than 1, right? Is there this cover y hat is 1? That's when it is greater than 1, right? Otherwise, what do we mean by otherwise? When y hat is exactly less than or equal to 1. So we added the point when y hat is 1 to that branch. Okay? So when we take the derivative now, it will be partial derivative. the derivative of the upper branch will be 0, right? Because it's 0. Now we are taking the derivative. Okay? So the derivative of the upper branch, which is this one, is 0. The derivative of the lower branch with respect to w, if you look at this, this is 1 minus yn w xn plus b. What is the derivative of this with respect to w? Minus yn xn, which is this. Okay? Type. Where is the subgradient? We are talking about subgradient here, right? Where is the subgradient? The subgradient happens when y hat is 1, right? Which is in which branch? This one. So now we acted as if this one is like that, and we computed the derivative at 1 with that line. So that derivative represents the derivative of this, and this will cover the case when y hat is 1. So now we have the derivatives for any value of y hat. So we acted as if this function is continuous. Is that clear now? Is it clear? Type. What if we want to change this subgradient to be like this? To act as if this line is continued like this. So we want to make y hat, the derivative at y hat to be 0. What should we change here? Yes, just add this equal here. That's it. We don't need to change anything else. In this case, the derivative will be 0. But the problem here is that we don't want to make it like that, because in this case, when the derivative is 0, if you remember from gradient descent, what will happen when the gradient is 0? What is the gradient descent rule, update rule? We have theta equals theta minus the learning rate times the gradient, right? If that gradient is 0, what will happen? There will be no updates at all. There will be no updates at all. We reached the global. Yes, it might be the case. Okay, it might be the case, but in this case, we don't want to stop the updates. We want the updates to continue. Okay, and that's why instead of adding it to that branch, we added it to the other branch. Okay. Okay, is that clear? Type. Any other questions? So this is what we call the subgradient. That's an example of subgradient. Of course, every case, every loss function that is not differentiable, we have to treat it in one way or the other. Okay, like what we did here. Okay, now how do we implement all of that? Yeah, let's say that we are done with, we studied the loss functions, right? We studied the regularizers, and then we studied how to actually solve the optimization problem using gradient descent. Now we want to train a model. We want to write an algorithm to train a model. How would we do that? So this is an example when we use hinge loss and L2 norm normalizer. Okay, so the loss function will be hinge loss plus the L2 norm normalizer. How we would train the model in this case. Right, what do we need to do to train a model now? We need the training data, right? First, we need the training data. So you'll see here that the algorithm takes the training data. So the D is the training data. Okay. Type. What is lambda? Do you remember? Lambda was the factor that was multiplied by the regularizer term. Okay, remember that the loss function had two parts. Had the loss part plus lambda times the regularization part. Okay. So lambda is a parameter here, and then the max iteration here is indicating how many times we'll go through the training data. Okay. Type. Let's go through this algorithm and make sure that we understand how it what is it doing. Type. Remember, what is the goal of this? What should we get out of this eventually at the end? The parameters, the model, right? We should, because this is training a linear model, we should get a linear model at the end. So if we jump to the last line, you will see that we should return W and B. So we will learn the values of W and B at the end. And W and B are the model that we will use for prediction. Okay? Type. Now, we will start with, without knowing anything about the actual weights, right, and the bias, so we will assign them, initialize them to 0. That's line number 1. Then you'll see from line number 2 to line number 9, actually not only 9, sorry, it is from 2 to 13. This is a loop, right? That goes from 1 to max iteration. So we will repeat the lines 3 to 12 max iteration times. Let's say 5 times or 10 times. Type. Now let's look at what we do actually inside that loop. What we will do is we want to optimize, right? We want to find the model, and we will use gradient descent. Type. Gradient descent needs the how to get the gradient, and then we update the parameters, right? These are the 2 steps. We need to compute the gradient, and then we update the parameters. Type. To compute the gradient, we need to know how to compute it. So we need to know the loss function. So in this algorithm, we assume that the loss function is Hinge loss, and the regularizer is L2 norm. So once we know the loss function exactly, we can compute, mathematically, we can compute the gradient, which we saw last time. We saw the last time the gradient, we saw an example, okay? And 5 minutes ago, we saw when we have an Hinge loss, what will be the gradient for the weights. So we have to pre-compute the gradients. I mean, not pre-compute in terms of numbers, but in terms of how to actually get the gradient. So here, the gradient is 0 if y hat is greater than 1, and minus yn xn if this y hat is less than or equal to 1. So we'll have to implement that. We'll have to compute the predicted value, and for one example, and multiply it with the label. That's y hat, right? So y is the label, 1 or minus 1, and wxn plus b is the predicted value. So we have to compute that with the current values of the weights and the bias, multiply it with yn, and see if this is greater than 1, what should we do? 0, which means nothing. We should not do any updates. If it's otherwise, then we should make the updates based on the gradient. And that's what we will see here. So, as you see here, this now inner loop goes from 4 to 9. This is going through, that's a loop over all training examples. So for every training example, we will compute, we will see if if y hat is greater than or equal to 1, is less than or equal to 1 or not, because that's the condition when we will update. So you see here the condition is y hat less than 1, less than or equal to 1. Then we will compute the gradient. Okay? Remember the gradient from the previous slide, what was it? It was minus y x. Right? You go back. It was minus yn xn. What is n here? N is the specific example. Okay? So here it is y x. Okay? Is that clear? طيب. This is just accumulating the gradient. We didn't update the weights yet. Okay, so we are just adding the gradient. We will accumulate it over all training examples. So what we saw before, what we learned before is that for one example, we can make the update, we can compute the gradient and then make the update, right? We can do that, or we can also do maybe do it in a more efficient way. We can compute we can accumulate the gradients over all training examples and then make the update once. So let me show you this. Let's say that we have, these are the examples. Okay, these are the training examples. Okay, for every training example we have the feature vector and we have the label. That's training phase, right? So we have the labels. So for every example we will compute, we will see what will be the predicted value and then multiply it with the actual label and see if it is less than or equal to 1 or not. If it's less than or equal to 1, then we should update the weights and the bias, right? So we should update here the weight, so we will have a new value, and the bias will have the new value. If y hat is greater than 1, then we will not update the weights and the bias, right? And we should do that with every example. Is that clear? Forget about the algorithm now. Focus with me on this part. For every training example, we compute y, we compute y hat. Sorry, not compute y. We have y, the actual label. We compute y hat, multiply them. If it's less than or equal to 1, then we update the weight and the bias. And then we go to the next example and so on. This implementation is a bit different. We compute, here we compute the gradient, right? We compute the gradient. For every example. In this implementation, we don't update the weights until we accumulate the gradient for all examples, and then we update the weights and the bias at the end. Once. And instead of updating the weights and the bias with every example, with every gradient, in this implementation we just accumulate the gradient, we add the gradient over all examples, and then at the end, after going through all the examples, we just update the weights and the bias once, instead of updating them with every example. Okay, that's for efficiency reasons in this case. Okay? And more stable actually, because some updates might cancel each other, so that would be more efficient. Is that clear? So now let's look back to the code, to the pseudocode. If y hat is less than or equal to 1, we will compute the gradients. So lines 6 and 7 are accumulating the gradients. Line 6 is updating the gradient for the weight, and line 7 is updating the gradient for the bias. And notice something that the author of the textbook decided. he used G bold to indicate the gradient for the weight vector, and non-bold G is to indicate the gradient for the bias. Okay, so these are two different variables. Okay, the bold one is for the weights and the non-bold one is for the bias. And you see that one is updated with yx and the other is updated with y, because the gradient with respect to the bias is just y, the gradient with respect to the weights is yx. Okay? Type. Now, looking at this line, line 6, what is x? Abir, what is x? The feature vector. Very good. The feature vector. So x is a vector, right? X is a vector. X is the feature vector for the specific, for the current training example. And y is the label, right? And the label is just 1 or minus 1, so it's a scalar. So a scalar times a vector is a vector. Okay? So actually here we are computing the gradient for, or the derivative for all weights. So this is a vector equation actually. In line 6, this is vector. It's not just a scalar. So G bold is a vector, it's not just a scalar, because it has the gradient for every weight. And we have a weight for each feature, right? In linear models, we have a weight for each feature. So that's a vector, but this is, the bias is just a scalar. Okay? Type. Now we said that the derivative, any question so far? Any question on this? Yes.
When we used to calculate the gradient and if it's positive or negative, we either add it or subtract it to make it equal.
Yes, let me explain this now. Okay? Because that might be confusing actually. Okay? Type. What should this be? If we are just accumulating the gradient, we should just put the value of the gradient, right? We should just add the value of the gradient. What is the value of the gradient in this case? It's minus yx. It's minus yx. So we should make this minus yx. So let's assume that this is a mistake. Okay? And just make this minus. Okay? And also this one is also minus, because the derivative with respect to the bias is minus y actually. Okay? Type. After we do this, we will update the parameters using the gradient descent rule, right? Which is this one. Theta updated with minus the learning rate times the gradient. Okay? So we should make it minus the learning rate times the gradient, and this one also should be minus the gradient, the learning rate times the gradient. Okay? Minus here and minus here is positive eventually. So what is written actually on the slide is correct. It's not straightforward, but it's correct. If we make both positive, it's the same thing as making them both negative. Okay, but maybe negative is more intuitive. It's more straightforward as we know the gradients and the updates. Okay, but both are correct. Either all of them are positive or all of them are negative. They are the same thing. Okay, did I answer your question now? Any other questions? Type. After we are done with the accumulating the gradients, we should update, right? We should update the parameters. So lines 11 and 12 are actually updating the parameters. So W is W minus the learning rate times the gradient, and the bias is the bias minus the learning rate times the gradient with respect to the bias. Type, what is this? And we covered all the lines now except line 10. What is line 10? That's the gradient of the regularizer part. Okay, so we are updating here the gradient with respect to the regularizer, the gradient of the regularizer part. Okay, so we are adding it to the bold one because that's the weights. That's the gradient with respect to the weights from the regularizer part. This gradient is just from the loss part. Okay, so we add them. Actually, if you change this to minus, then you should change this to plus. Okay. Because actually the actual gradient with respect to the regularizer is plus the lambda w. Okay. Type, when will we return back with the model that we learned? The parameters of the model, yes. Okay, but when are we done? Yes, when we are doing maximum iteration over all training examples. Okay, that's the outer loop. So the inner loop goes through the training examples all once. Then that's the inner loop. The outer loop goes multiple times. Any questions about this? Type, what if, and let me ask you, what if we change the loss function? Can we use the same algorithm? Yes?
I think that the only part that will change is updating the gradient since we
Which lines?
6 and 7.
And 10, if we change the regularizer also, right? So yes, so what we will change is the lines where we compute the gradients. Okay? The others are not. And also line 5, because it depends on the loss function when we will change the gradients. Okay. Fine. Any questions? I think we spent a lot of time on this, right? But what will we do with this after we are done with training? خلاص يعني we are satisfied now. We train the model. What should we do with it? Huh? We can test it. We can use it in prediction for unseen data, right? Now because we have the weights and the bias. How will we use it? And now I have a vector of weights and the bias. Okay, how will I use it for prediction? It's a linear model. Do you remember how the perceptron works? That's the line. Okay, now if the weights, now we get a prediction, right? For any point, any new point. Let's say that I have a new point x. Sorry. Let's say that I got a new point, a new feature vector, x star. I want to compute the prediction for x star. What should I do? What should I do with this is the model, right? These are the values of the parameters of the model now. How can I use that to compute a prediction for x star? Exactly, yes. Yes, but how can I do it in reality? Right. Look at this algorithm. Where is the prediction here? Don't we actually compute a predicted value and compare it with the actual value in some way here in this algorithm? Where is the prediction? Look at the algorithm and tell me where is the prediction here. Do you remember Perceptron? In Perceptron, we update the model when it makes a mistake, right? Here we update the model when the prediction times the label is less than or equal to 1, not 0. It was 0 actually in Perceptron. Here it's 1. Where is the prediction? I just said it, right? Line 5, where exactly? What is the term that tells us about the prediction? Which term of these? Where is the, can you tell me the expression of the prediction? Yes, Wx plus B. Wx plus B is the predicted label. So W, I will multiply x star by W and then add B. Now this is the predicted value. If this is greater than 0, then I will predict positive. If otherwise, I will predict negative. That's a linear model now.
I got everything confused. Where did we get it? Okay, so the bias is fixed and the W.
The bias is fixed and the W is not fixed. I don't understand.
We get the parameters, weights, and the bias.
Yes, yes.
Which weight are we going to use for this one?
Okay. Which weight? Type. How many parameters are there? Very good. Yes. And x star is a vector also, right? So this is a vector. No. That's a vector, that's a vector. Vector times it's a dot product, so it's the outcome is the scalar. Plus b, it's a scalar. So this is a scalar. That's a predicted value. So if that predicted value is greater than 0, then it's positive. Then I predict it's positive. Otherwise, I predict it's negative. That's how I will use any linear model, by the way. It's not only the one that we trained here. Any linear model, once I have the weights vector and the bias, this is how I use it for prediction. All of them. And Perceptron was just a special case, just an example. Actually, I have it in the next slide. By the way, this is anything wrong here, it means that the note that I told you about, the G bold and non-bold. Okay. Here's Perceptron. That's exactly the algorithm that we saw maybe a month ago. Okay. If you look at it now, you will see that this is just very similar to the algorithm that we saw in the previous slide, with some changes. And the changes here is because Perceptron is using a different loss function than the one that we saw for the previous slide. Okay? And the question is, what is the loss function that Perceptron is optimizing? And I will leave that to you. So you see the connection now? So every linear model actually has a specific loss function, and we can, with optimizing the loss function, getting the gradients and using gradient descent, we can have a specific algorithm like that. Okay? So you can look at the algorithm now and see what was the actual loss function that this algorithm is optimizing. Okay, summary of gradient descent. It's a general algorithm to minimize objective functions in general. We used it specifically here to optimize loss functions for linear models, but it is general. It works well as long as the function is well behaved, which means it's convex, but it can also work with non-convex functions, of course, but it's not guaranteed in this case to find the global minimum. And we can use subgradients, of course, at the points when the derivatives are not defined. Can we do better? Do we have to use gradient descent in all cases? Actually, in some loss functions, they are convex, and thus we can find, mathematically, we can find the closed formula for the values, for the best values of the parameters. We don't need to go to do it using gradient descent iteratively. Okay, there are some loss functions where we can mathematically compute the best values for it. Okay? And you can find an example of that in section 7.6 in the book. And you can look at it. It's optional. It's not, you are not required to look at it, but if you are interested to see a closed formula for a linear model using a specific closed function, you can find the example here. Any questions? Was it an easy lecture? If you understand, it's easy, right? If you understand. If not, it looks very complex. Any questions?